In the name of God, the compassionate, the merciful, Engineering Plasticity, Chapter 2, Stress Analysis, Part 5. The principal directions could also be found. In previous slide, we proved that sigma 1, sigma 2, and sigma 3 are all perpendicular to each other. It means that their planes also is perpendicular to each other, and we obtained this relationship obviously from previous slides. L1 sigma x6 minus sigma 1, m1 sigma x6 plus n1 sigma xz is equal to 0. Remember, we had these equations. Instead of sigma 1 in here, we had sigma. Now we have put instead of sigma 1, because for sigma we can put sigma 1 or sigma 2 or sigma 3, because we have 3 planes. So we have 3 sets of equations like this. For sigma, 1 set for sigma 1, 1 set for sigma 2, and 1 set for sigma 3. Now we want to find out the directions for each of these planes. How do we do that? Okay. Now these equations also we obtained very easily, and we could do it again, like eliminating n1 from these equations and get L1 over n1, and eliminating L1 from this equation and get m1 over n1, and also L1 over n1. Therefore, we have here 3 equations or relations between L1, M1, M1, N1, and L1 and N1. We also have this relationship, okay, which is for the direction cosines of any lines. So L1 squared, M1 squared, N1 squared equal to 1. The sum of these is equal to 1. So we can use these 2 relationships easily to obtain L1, M1, and N1. And so in this way the direction cosines for the principal directions are known, and we know where the direction of that plane is for sigma 1. Similarly, for sigma 2 and sigma 3, we can do similar operations to obtain the direction cosines L2, M2, and N2, and therefore in this way the 3 principal planes are determined. Now the general stress state on the W oblique plane could be determined in terms of the principal stresses. We said that this is an arbitrary plane. So this is not a principal plane because it has a shear stress and normal stress. Okay, so normal stress is like that. It's not sigma 1. Normal stress is something perpendicular to this plane. Now, what are these sigma 1 and sigma 2 and sigma 3? These are the principal stresses. Okay, it means that if we change the directions of this W oblique plane, we could get sigma 1 perpendicular to it, or sigma 2 perpendicular to it, or sigma 3 perpendicular to it, if we change the directions towards sigma 1 and sigma 2 and sigma 3. But here where we are, it's arbitrary plane, it's W oblique plane, and it's not perpendicular to any of them. But now we want to find out this S, to determine this S in terms of sigma 1, sigma 2, and sigma 3, because we have so far determined S in terms of SS and Sn, in terms of Sx, Sy, and Sz. Now we want to find out in these terms of sigma 1, sigma 2, sigma 3. Okay, so we get back these relationships from previous slides. Here I've come back to this slide to show you why we are putting Sx equal to sigma times L. If you remember, we said that principal planes are the ones on which the shear stress is 0. So in here, in these equations, remember what these were. This was the component of stress in the x direction, and we said that component of the S in the x direction has a shear value and a normal value. So if this normal value times cosine alpha or L gives the normal component of Sx, and Ss times Ls gives the normal component of Sx. Similarly for Sy and Sz, we get normal component, shear component in the y direction, and normal component and shear direction in the z direction. And then because the shear stresses are 0, we put Ss is equal to 0. So we get Snl is equal to Sx. What we said like that, Snl is equal to Sx. But instead of Sn, we put sigma, because we said for the condition that the shear stress becomes 0, Sn becomes the principal stress. Therefore, we put, instead of Sn here, sigma, and similarly for the other ones, and then we get this relationship. That's why we could write these relationships, okay? Sx equal to sigma L. Previously we put sigma L, but here we are putting sigma 1, 2, and 3 because we have these three principal stresses. X is sigma 1 L, sigma 2 M, sigma 3 N, and sigma XX is sigma 1, sigma YY is sigma 2, and sigma ZZ is sigma 3, okay? Because these are we are saying that when we are talking about the principal directions, then we have only one principal plane which is perpendicular to that direction, and we have written these here in terms of sigma 1, 2, and 3, which is Sx, Sy, and Sz. Now we are writing, instead of Sx, we can write sigma xx times L. Then both L's cancel out, and we get sigma xx equal to sigma 1, sigma yy equal to sigma 2, and sigma z equal to sigma 3. Shear components are 0, and we have 6 shear components which are equal 2 by 2, so we have 3 components equal to 0. All the 6 components are 0, and we had this relation before, S squared equal to Sx squared, Sy squared, Sz squared. Now we put substitute for Sx, Sy, and Sz, so we get this relationship. S squared is sigma 1 squared L squared, sigma 2 squared M squared, sigma 3 squared N squared. And here also for the normal component of the stress, we had this. Therefore, if we substitute for Sx, Sy, Sz in these 3 components, then we get these, and that's the normal component of stress in terms of principal stresses. Also the shear stress, shear component of the stress, we could write down for Sx, Sy, Sz from here, and we get that. Okay, so as you can see, we can have the total stress in terms of the principal stresses. We could have the normal component of stress in terms of principal stresses. and we can have the shear component of stress in terms of principal stresses. So we have obtained what we wanted. So in here, SS squared is S squared minus SN squared. We had this before. Okay, and S squared is this one, and SN squared is that one. So SS squared, if we substitute these two in here, we get this. Okay? And if we rearrange these components, we get something like that. Sigma 1 minus 2 squared, L squared M squared, sigma 2 minus 3 squared M squared N squared, and sigma 3 minus 1 squared N squared L squared. Now you can see something similar here, can't you? I mean the yield strengths, okay? The yield function, you remember? We had in yield function sigma 1 minus 2 squared, sigma 2 minus 3 squared, and sigma 3 minus 1 squared. We had this in the yield function when you were studying your BSc. If you remember, we had this before. So, and this is the shear stress. And we have said before that the plastic deformation happens due to shear stresses only, because slip planes, slip directions are activated because of the shear stresses. If we don't have any shear stress, then we don't have any deformation. So once again here we can see that all these stresses, which are principal stresses, they will cause this shear stress, which will cause the deformation, as we have said before. Here are some examples for the stress states in terms of principal stresses. Okay, the first example is a very simple one, which is a uniaxial tension. As you can see here, the matrix is given, and we only have one component. Sigma bar is equal to sigma 1. The other components are 0. Obviously, we have non-components of stress. Biaxial tension also is a simple state of stress, but it has two components of stresses. Sigma 1 and sigma 2, both of them principal stresses. As you can see, the sigma bar is equal to sigma 1 and sigma 2 in the diagonal part of the matrix. The rest of the components are 0. And here we have a three-dimensional state of stress, which is hydrostatic pressure. In fact, the stress is pressure here, and as you can see, the stress components fill in the diagonal of the matrix, and the rest of the components are 0. In hydrostatic pressure, obviously, we have pressure applied to the body from all over the place. Here we have opposite to the hydrostatic pressure, which is triaxial tension, and the component of stress here are positive.